Hello, Professor. I'm here to explain my code for the assignment for heap and priority queue. So basically, we are asked to create a linked heap, implement these three methods, and based on that, we need to create a priority queue using that heap structure, that linked heap structure we just created, and implement these 5 methods for that priority queue. So basically, we will need all these 8 methods in that linked heap. Let's see my code. And after that, we're gonna use this test case to test the priority queue. And I noticed that there are 2 tester files provided in the homework link. So I took the liberty of testing the code I write using the tester function it provided. Let's see the code. So let's kill the current, rerun, and restart and clear all the output. So yeah, let's compile again. So this is a binary queue, linked heap I created utilizing the binary node provided. Let's run it. Okay, it compiles with no exception. And this is a linked heap tester provided with the homework. And I noticed that although in the requirement it's asked to test with integers, this tester requires the data to be a key value pair, right? To be key value pair, right? So when coding it, I set the data to key value pairs to accommodate with the tester. Let's run the tester to see it goes without exception. Yeah, here we can see the tester succeeded, proving the code works. And let's go into the code, explain how I did that. And the heap. This is a class provided using the simple structure of array, and we're supposed to use linked list to create linked heap. So this class is, to be honest, not much of a use. But from here we can see we're still gonna need this float method, insert method, sync method, mini child, and poop. And poop in our case is delete or remove. So we can see float is to move a node up to its correct place. Sync is to move a node down to its correct place. And insert, we're gonna insert a new node to its correct location, utilizing a binary path of that location. And in this method, we get the minimal child of a given node. And this method, we delete a node, which is actually pop. And to pop a node, we actually removing the root of this tree. So after remove the root, we put the largest element of the tree to the top to become the new root, and we simply need to sync that node to its correct location utilizing the sync method we just shown earlier before. And to locate this largest element of the tree, we utilize again the binary path method. So this is delete. And pick. So we can pick without removing the element. And now let's explain a little bit how the binary path method works. So since the tree is binary, so at each node, whether the node is with a given index is at the right child of or left child of this node, it can be determined by if the subtree rooted at this node is balanced or not. So take example of this 3-level tree with 6 elements. So for example, we need to find the path to F. So in our case, we need to pop an element, or we need to move the last element to the top of the tree. So in both cases, we only need a path to the last element. So for example, in this case, F with an index 5. So we'll find 5 is a odd number. So the first layer F must be located on the right subtree of this root A. And so how many elements will there be in this right tree? We simply divided 5 by 2, and the number we get is 2. So there will be 2 elements in this subtree. And how many elements will the subtree and we divided 2 again by 2. We can see this 2 is a even number, and we can see the F will be indeed on its left side. So here is the algorithm. So each time we divide it by 2, and to find it's on the left child or on its right child, and we construct this array called path. And to find a node using this path, we simply go to if the number in the array is 0, we go to its left child. If the number is 1, we go to its right child, and by that we get the element in the tree. And to swap, and this function we swapped parent and child. When we reorder the tree, we might need this function in that think and float method. So to swap a parent and child, there will be 4 steps. First, we need to keep track of the parents, and then we put the parent under the child, and we put the child over the parent, and we link the parent's parent to the child, to the child. And this function is a length function. This function is here because the method is required by the priority queue. We'll show later. And we can see this is a test case. This is basically the linked heap tester, which we have run past. Okay, so that is a part of the priority queue part. And now that's the linked heap part. Now we go to priority queue. So we basically have all the methods already implemented. So for the class priority queue, we just need to use this subclass. We just need to use this use the method in linked heap. Alright, so we have as requested, we're gonna have a add, remove, a minimum, and the method to test if it's empty, and finally the method to get the length of the priority queue. So as requested, we're gonna test by adding these 7 integers to the priority queue. Again, we coded to accommodate the linked heap tester. So the elements are going to be a key value pair. So here we're gonna need to insert those elements as insert those integers as key. So we run this and dequeue 3 times, and we can see the element dequeued are 4, 5, and 6. Indeed, what we should get. And again, we can use the priority queue tester to see if other functions are working properly by this throughout test. And here we can see it works. So here's the demonstration of my code. Thank you, Professor.